So let's just keep going from where we left off last time. So just a matter of a couple of comments of things that you should see. You should have seen homework 0 has gone out. It's just a shorter homework designed to get you kind of into the swing of things, make sure you know how to use, review some ideas. Also, make sure you know how to use PyTorch and things like that. So that's the goal. You've experienced the first discussion section. So I want to make a comment about discussion section. So remember, so for some of you are graduate students and you might not be used to the idea. Maybe in your original school there wasn't a discussion section. So discussion sections in this course cover mandatory material. Like the material covered in discussion is required for the course. So it's basically a chance for you to understand the material in a more interactive way with specific problems in front of you, and where you can get help from course staff and work in groups. So we noticed that in the attendance at the discussion sections from graduate students in many sections was quite low. So I want to encourage grad students to do try to come to discussion. It is important. For undergrads, the discussion sections are very valuable. We're not taking attendance, but in our experience, people who attend discussions regularly and participate actively do far better in the course on exams. So we do want to encourage you to do that. Come to discussion. It'll happen every week. We will release a homework 1 soon, ideally today or tomorrow, and kind of get back onto the Friday, our regular Friday due date cycle. And homework 1 will also have substantial review, given that the lectures are also, first few lectures are largely review. Okay, so we're just going to continue where we left off last time. So last time we talked about the idea, which is amazing, it's still on the board, that when we're doing these optimizations to figure out how to set all the parameters in our model so that we can generalize well, the optimizer might have its own hyperparameters like a learning rate. This gives us a kind of chance to talk about the idea of learning rate and what happens. So the idea of gradient descent optimization, so here I'll just mark things that are vectors as vectors. We have lots of parameters, so think of them as a big vector. We evolved the parameters based on the training loss. So we look at the training loss, and we compute its gradient with respect to the parameters, and then we take a small step in the direction opposite the gradient, because we want to reduce the loss. So this is basic gradient descent. And if you look at this, this is coming from, we mentioned last time, it's coming from the perspective that we're going to look at the training loss locally. So we think of the training loss as a function of where we are, but we want to understand where it would be if we were to take a small step. And so by doing a Taylor expansion view of the loss, we see what the dependence is on the parameters. And so we can then figure out what direction to move in, okay, to maximum. We want to make this as small as possible. It means we match these two together. So this is the, and we commented there that, because this is fundamentally a dynamic system, that this is evolving with time t, which is an internal computational time, we have to worry about the stability of it. And in general, if the learning rate is too large, the dynamics will go unstable. But if the learning rate is too small, it'll take too long to converge. So that's where we ended last time, kind of in this discussion. So we closed with the idea of thinking about, okay, so we care about getting this learning rate right so that we converge. And we mentioned the idea of wall clock time. The idea that it's really important in these problems that things actually work not with some abstract iterative time, but with actual time on the clock, right? Because that's dollars of compute. And so in doing that, that's like an excuse to talk for us to talk about stochastic gradient descent. There's another review thing we have to do. So you look at this training loss, and the training loss has a big sum in it, right? Because you're summing up over all the training examples you have of this loss. So, you can use, when you compute this derivative, right? This derivative, it'll play nicely with the sum, right? You can just bring it inside the sum, but you still have to deal with the fact that you have a lot of terms here to work with. So, computing this gradient here, requires computing this loss typically, and it can become expensive if you have n large. So what can you do about this? So the standard approach that one has to think about, making this part more friendly with respect to wall clock is to use stochastic gradient descent, SGD. And the idea of SGD is to say, instead of using n, all the training data, just randomly sample it. Just use n batch, typically much smaller than n, random samples. So when you use n batch, what you'll use is an approximation of the training loss, and hence an approximation of this gradient, where instead of everywhere you had an n, you instead use n batch. So this n becomes an n batch. This becomes an n batch. And then these i's become, xi. These yi xi pairs become a randomly drawn n batch number of training points. Ideally, kind of our mind, how we think about it. So when you do that, you're replacing something which is an average of a lot of things with an average of a smaller number of things. And so you expect that this will be an unbiased estimate of that quantity, right? Because just a randomly drawn subset has been selected. Yeah?
Will the same data be sampled multiple times in the same apple?
Okay, great. So I'll talk about that in a moment. So the question was, what is going on here? So I'll say it this way. Wait, you have n training points. So how do those training points get hit if you're randomly drawing from them? So here we'll talk about that in a moment, kind of at the next level of detail. We're supposed to understand the basic level of detail. So the basic idea here is if you were to do a random draw, you get an estimate of so the quantity you're interested in is an average. And if you take a random draw of points instead of the entire set of points, you will get an estimate of that average. That estimate will be itself on average. If you were to go over all possible things you could have drawn, it would be the right thing. But it will have some variability associated with it because the fact you're taking a small number of samples and not a large number. So before we talk about kind of the next level of detail, let's understand philosophically and make sure we recall for everybody philosophically, why is this okay? Why is this reasonable to do? So there's many answers here. And one answer is the standard deep learning answer, which is I can't afford to look at all the points. I can afford to do this, so I'll do this. Okay? This is like a totally legit answer. But we can go a little bit further in our understanding. And so a little bit further comes a depth of understanding comes from the idea that, look, when we're going to be moving this theta, there might be different regimes of where we are. And when we start off, we have no reason to believe that where exactly we start off is going to be a good place. So probably in this thing, there's lots of these points that are all going to be telling us to move in a similar direction. So why do I have to exactly compute that direction when I'm going to have to take a step in a certain direction? Maybe a small number of points will be definitely enough to tell me what general direction to move in. So I don't need precision beyond what is required for me to take my step appropriately. So that's a particular intuition that's pretty reasonable. It's good to keep that intuition in mind as you think about, like we talked about this hyperparameter, which is learning rate, which is how you might think about how this learning rate might change during our training. So the default answer is you pick one learning rate, you stick to it, which is also not that bad. But sometimes you might want to think about how that learning rate might change during training, and think about what's called a learning rate schedule. So understanding the intuition of what's going on is helpful to think about, help you understand what's going on, what might be going on with the learning rate schedule. So that's a reason why you might believe this will work. It's actually kind of interesting that there is alternative perspectives which most of you might not have seen in a standard machine learning class, which is why I'm not going to dwell on it here. But for those who are interested, you might be interested in looking up the area what's called online learning, which is learning from data that is revealed to you sequentially, one after the other. And there's very interesting, beautiful analysis of online learning. It's somewhat surprising, which also argues for another reason why these kind of approaches, looking at only a small set of data, still work. Okay, I'm not going to dwell on that here. It's not to say that online learning isn't relevant for deep learning. It actually is quite a bit, but not at this current stage of coarseness of description that we're doing. And also, it's not something that I expect everyone to have seen. Yeah, question?
So when you have like a step size for regular gradient descent, and let's say like the divergence or convergence, does it also imply the divergence or convergence at gradient descent as well?
Okay, that's a great question. So I'll repeat it. The question is, if you have a step size that you know will converge for regular gradient descent, does that mean that that same step size will also behave well for stochastic gradient descent? Okay, so it's a really good question. So the general answer is no. Okay, that's not necessarily the case. The reasons why are a little bit subtle, but I can give you the basic idea. So you can think about two things. First thing is, if eta is too large, then dynamics go unstable. When it comes to going unstable, like actually like exploding, then yeah, because the averaging is the same size and the expectation is the same way, you expect that the same thing will roughly work in terms of stopping you from exploding. However, what you actually need to have happen is you need your model to train and converge to something that's good. Okay? So when you do that, and this is actually pretty subtle and delicate, I'm going to give you first the conventional answer that probably most of you have seen. So I'll poll you afterwards to see who has seen this, but if you have. So the conventional answer goes like this. Look, if you need this thing to converge, okay? What does that mean? What does convergence mean? It means that this thing stops moving. Time keeps going, but this is no longer moving, or not moving by very much. Okay, everyone, that's what convergence is. So what would make it move? This? No, that's the last thing, so that's not making it move. What's making it move is this part. So standard kind of optimization thinking with the actual gradient says, look, when you're at a stationary point, which an optimum definitely is, at the stationary point, the derivatives are 0. Right? There's no more variation, no more little movement won't change anything substantially, so the derivatives are 0. And so that's why you converge, just because you're approaching that point, and so this thing is approaching 0, and so this, which is where you were, plus something which is approaching 0 means that this thing is staying still. Got it? Okay. Now, that works for gradient descent. But let's think about stochastic gradient descent. In stochastic gradient descent, you are not using all the training points. You're using a subset of training points. So the classic picture you should have for this is something like this. You want to least squares fit a straight line to a bunch of points. That's what your least squares fit looks like, right? Like a straight line. But notice something. Your losses are a bunch of sums of squares. Right? Every individual term is a bunch of sums of squares. And so at the optimum value, this, although the overall gradient of the loss is 0, the corresponding component that corresponds to this point is not 0. Does everyone see that? Because this point isn't fully happy. Right? This point would prefer this line to move up. The overall gradient is 0 because of a balance between these points. So some points are tug of war. Like this is the key thing in deep learning, in all neural net, in all gradient-based learning generally. What you have is a tug of war between points. Some points are pulling parameters one way, and other points are pulling parameters the other way. Classical perspective. And so the final answer you get is the balance point when everyone is balanced. So if you were to have, you were actually to be at this optimum thing, and you were to run not gradient descent, but stochastic gradient descent, what would happen? What would happen is that a small number of points, whichever ones you randomly picked, will likely have some imbalance in their pulling, in their tug of war. Does everyone understand that? Because everyone together balances. So a subset only kind of balances. And so what will happen is that for SGD, this term will not, at optimum point, under the classic perspective, will not go to 0. And so what will happen is that if this learning rate is anything which is itself not decaying, this thing will only kind of converge. It'll like converge something, sort of, look like it's converging something, and then it'll do a little dance. Wiggle, 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 wiggle. Keep wiggling, right? Because of this stochastic variation that's happening from the SGD. Right? Did everyone see that? And so, under a classical treatment, which I hope people have heard about, of SGD and its convergence, you would have for SGD to have actual convergence, it's not sufficient for eta to simply be small enough. It actually, at the end, has to be diminishing to actually get convergence. Okay. Question, yeah. Okay, that's a good question. The question was, do we typically have n batch, the number of points we pull, change with every iteration, or do we keep it the same? Okay, good. So let me answer that question. It's a good question. So first, does n batch typically change during training? And the answer is no. You usually pick something and stick with it. Why do you pick the thing you pick? Typically, you pick the thing that is the biggest batch you can sustain given the parallelism and memory of your architecture. So you want to make sure everything fits in memory and you don't get cache misses and other kind of crazy nonsense happening. So you pick a batch size that'll fit, and then you use that. Because that will be the fastest, because what you care about, again, from the deep learning motivation, which is not a theoretical motivation, it's like, I want my wall clock time to not be too big. Okay, so you go for the batch sizes that will make your wall clock time the best. Okay, now your question. Your question was, if you just picked a batch size, let's say 7, okay, 7 things.
Just a batch size of the same thing and sim.
Okay, great. That's good. Okay, good. That's exactly the distinction I wanted to make. So you pick this batch size, but then every time you take a step, you draw fresh samples. So it's always, that's why it's shaking around, is because you get a differently imbalanced tug of war in a small group. Small groups will never balance. They will always be imbalanced. Okay, does that answer all your questions? Okay, good. So this is the classic story. So now I want to ask kind of a poll. How many people have seen this classic description of why SGD requires a diminishing step size for convergence? Raise your hand. Small number. How many people have not seen this description of why SGD requires a diminishing step size for convergence? So for people who have not seen SGD requires a diminishing step size for convergence, does anyone want to volunteer for whether, so first of all, how many people have heard that you should have a diminishing step size for SGD? Okay, so there's an overlap between these categories. So for people who have heard that you should have a diminishing step size for SGD, anyone want to volunteer for what explanation you have heard for this? I just want to know where my class is for the explanations. Yeah.
Maybe the gradient may become smaller, then if we keep the same step size as before, then you will do some very random point, but never go to the optimum point that you want to be. You will never be there.
So it's unclear to me, so I'm not going to repeat that, but it's unclear to me why the fact that the gradient becomes small will make you do a wandering. What's that bridge?
Because if you go to a large step size, then you will cross over the minimum point.
So that's why you're not too big. So the question is whether you've talked about why you would want this to the step size to keep becoming smaller and smaller and smaller. That's what I want to know. Who's heard an explanation for that? Just because I want to understand where my class is. Yeah.
Initially, when we're further from like the optimal, we can take will be easier. Slow it down.
Okay. So the answer was that when you're far, the explanation some people have heard is when you're far away, you can afford to take a big step. But when you're close, you don't want to miss it or go unstable, so you go for a smaller step. Is that kind of what you're saying? Okay. Have other people heard that explanation? Okay. Anyone with a different explanation for what is going on that you want to talk? Yeah.
So I learned about this in the traditional graphic sense, where you have like circles, concentric circles, the behavior of gradient descent of stochastic acid convergence. And what you see is stochastic is it zigzags towards the center. And the explanation for diminishing values is that as you go through, like you interpret the error. You basically interpret the stochastic feature as adding noise or adding some error at every single step. And so you want to diminish that so that that error shrinks to zero as you approach actual minimum.
Okay, so that explanation is the same as the one I said, right? That the stochasticity of the small batch is what's causing you to wiggle, and so you have to suppress that by making this get small if you want this thing to actually converge. So good. I want to make sure that people also understand it. Yeah, one should make a distinction. It's good for people to remember. Make a distinction between oscillatory behavior of bouncing back and forth and random walk behavior of being shaken about. These are actually different. Both occur in the context of the analysis of gradient descent. Both are combated with things that might look similar, but they're different behaviors. Yeah.
I can't think of like anything that I could thought of. One thing I was thinking is there any connection between this and like, the eigenvalues of the gradient?
Yeah, okay, so the question was, is there a relationship between the understanding of the step size and some appropriate eigenvalues? And the answer is yes. In the analysis of classic standard gradient descent, this threshold between stability and instability is exactly tied to eigenvalue analysis. But in the context of stochastic gradient descent, it is more subtle. Okay, because you have to think about eigenvalues of certain random matrices and how they behave. But there is still a relationship. So there's a second explanation, which I was thinking maybe some of you have seen, of kind of another like analogy, which is also good to know. Suppose I wanted you to compute the average of 10,000 numbers. Okay? But you would be shown these numbers one at a time. Okay? How would you compute the average of 10,000 numbers being shown them one at a time?
Well, you can compute those about. Well, basically, you can update the average, and there's an equation. I forgot the equation. The original one.
Yeah, the answer is you can update the average, right? So you keep this is like you have very limited amount of memory. You keep the average, and then you get a new point, and you know what point it was, like this is the 37,000th point. You're told that. Then you can use that to update the average. Okay? And if you do that, if you write out those equations, which is a good exercise if you haven't done it already, and it's sometimes done in some classes, you'll see that the amount that you move the average with every new point becomes smaller and smaller and smaller. That when you have 2 points, the second point, it moves the average quite a bit. But when you've already seen 999 points, the 1,000th point moves the average only a little bit. So that's also a reason, kind of inspirationally, for why this step size is getting small. So this is a useful side thing to make an aside comment that is useful in the context of deep learning. Whenever you find yourself feeling lost or confused or like wondering what is going on, okay? What you should do in the context of machine learning is close your eyes. It's like, like on a ride or something, close your eyes and repeat to yourself, it's all just fancy averaging. It's all just fancy averaging. Okay? Because actually, that's kind of what's going on all the time. So everything that happens, that whenever learning works, it's all just fancy averaging and low-pass filtering. Okay, that's literally, it's some like disguised version of this with all kinds of other sophistication. So if you find yourself confused about anything, you can say, okay, let me see if I can see which way averaging is. Some familiar landmark that I understand very well, and like make the connection between what's going on here and some kind of averaging. And that might help you orient yourself for what's going on. Okay? So SGD is like fancy averaging, but it nicely works. So I told you that I was first going to talk about this in the classical point of view. So now I'm going to give you a preview of something that can happen. We'll talk about it. We'll keep coming back to it in the context of deep learning. So in deep learning, sometimes what you see isn't like this picture at all. Instead, what can happen is that your gradients will go down because every single one of your points will start to become happy. It won't be that your training points are all unhappy and in a visible tug of war where some are, okay, I'm this unhappy, but you're that unhappy, so okay, we can't move the parameter. It's like everyone's like, I'm good, I'm good, I'm good, I'm good. Okay? Which is a behavior which is different than what happens in classical settings. But it will happen in deep learning settings all the time. And so in those settings, what will happen, and I can't draw a good picture of it for you yet. I mean, here, right? We understand this a little bit, but not sufficiently for me to draw it in very short term. What will happen is that your n batch points will all be reasonably happy as you keep going in training. And then this gradient will become small. And in those cases, you will see that even SGD with a constant step size will converge. So in practice, for many deep learning applications, despite the fact that you've been taught, and we talked a little bit about the classical story of making sure your step size is diminishing, the learning rate schedules that we will sometimes use will end with a constant learning rate. We will not have a diminishing learning rate, and it'll still work. So I wanted to warn you of this discrepancy between what you've seen in your machine learning classes and your optimization classes and what you might start seeing here. Okay, with all that, now I can come back to that next level of detail that was asked for earlier. So the way I described it was the kind of conceptually easier way, which is every time you take a step, you draw n batch random training points and use them. However, remember, what we care about is wall clock time. And this can become painful sometimes with respect to wall clock time because your data set might not fit even in, not your GPU memory, but they might not even fit in your regular memory. And so doing a random draw and then doing disk seeks to different points to get your data is too painful. Okay? So what is often done is a different strategy where you say, you know what? Sampling with replacement and sampling without replacement for a large number of points is kind of the same thing. So let's just sample without replacement. So what you do, practically speaking, is you take all your data points and you shuffle them. The shuffle is kind of really, really important. Shuffle them randomly. And then just look at them n batch at a time. So when this kind of approach is done, there's some specialized terminology in the deep learning community used to refer to things. So here, people at the beginning were very, very concerned about whether or not you've actually seen all the data. And so they would refer to the times that you've actually gone through this entire batch of data, all the data you have, as an epoch. So you go through the entire data, in the shuffled way, that's an epoch. And then you do it again. Now, here, you can, in principle, and if you want to avoid certain kinds of subtle bugs that sometimes happen, you might want to do this. You might want to reshuffle your data between epochs, just to prevent having some pattern repeat and bother you. But many people are like, that's too annoying, and so they just won't. You just shuffle your data once and just keep using it again and again. It's a balance between avoiding certain subtle weird bugs that can happen and wall clock time and implementation complexity. Yeah, question?
Sampling with replacement yield better results?
Will sampling with replacement yield better results? The answer is no, typically not, because what will happen is relative to each, so if n batch is sufficiently small, then for every one of these steps that you're taking, the difference between sampling with replacement and without replacement is almost nothing. So it turns out not to make a big difference at all. Again, this will give you a little bit of a bias. The bias in this course and in a lot of deep learning research, unless we state otherwise, will be to cases where you have a lot of data, like lots, thousands plus. When your data sets are very small, then different levels of care might be required, because then you do see differences between these things. Yeah.
What do you normally suggest for the meaning of n batch much smaller than n? Meaning like the order of 10 or like order of 100?
Good good question. The question is, when I write n batch is much smaller than n, what should this be? The answer is n batch should be as big as works for you in deep learning practice. N batch should be as big as works for you with your hardware. Fast. Okay, and that will depend on the problem. It'll depend on your hardware. That's what it is. So n will usually be like much bigger, but you have no hope of getting there. So this is something that you can hope to get to, and you go get there. Now, there's an entire other part of the subject that we are not going to do more than maybe touch on here and there, hint at, which is which you can think of as the classical CS point of view on deep learning, which would be, look, you have massive quantities of data. You have to marshal not just, you have to deal with the details of the computer architecture that you have, and the memory and networking systems that you have, and the distributed storage that you have in real world systems to actually get these things to work in an accelerated way when they're very big. Okay, so this is like something that is usually referred to as ML systems. It's extremely important in practice to deal with wall clock time. And when the large companies that exist all have teams of very highly paid people who figure out how to manage those systems and to get them to work. And the algorithmic design sometimes takes the considerations of those systems into account. Because if you can't scale it and run it on large enough amounts of data, it won't give you the right performance on wall clock time and dollars. So you have to choose an architecture that does. That entire level of consideration, we are not going to be talking that much about. For one simple reason. We have no way right now that we understand how to give you homework about it. If we can figure out ways of giving you homework that hints in that direction, we might start putting some of it in. But we don't know how to do it, so we're not going to spend time on it. Okay, so this is like a longer than I expected review of SGD. Any questions on that people have? Any remaining questions on basics of SGD? Okay, so now you understand what you think is the basic perspective on why things work, kind of the way that people normally understand it. We are going to challenge it a little bit in a little while. But for now, let's just be happy that we've kind of caught up on where we are, where you were from your ML class on the big picture. What I want to do now is to just remind people a little bit about just neural nets themselves, since this is a class on deep neural nets and we haven't really talked about neural nets yet. So what's a neural net? There's many different perspectives, and there are people who come at it from a biologically inspired point of view. We already said before, it's some kind of analog circuit that you feed data in, it processes in an analog way, you get analog outputs, and you interpret them. That's for sure true, but the question is how do we think about that? And what's the point? So I like to think of it not in a biologically inspired way, but instead in keeping with the general spirit of deep learning, of you do what you know how to do, it says, look, we know how to optimize things using gradient descent and stochastic gradient descent. What kind of computational thing makes it easy for us to use gradient descent and stochastic gradient descent? Whatever that is, let's use that. Okay? So so I'm going to assume that everyone has seen neural nets before. This continues to be review. Okay, I'm just going to give you a slightly different perspective on it. So you know that you can compute derivatives using gradient descent, using the chain rule. And you know that computers can do the chain rule for you. And so computers can do automatic differentiation. So for us, a neural net is anything that plays nice with automatic differentiation. Okay, so it's a computation graph. Circuit. Analog circuit. Plays nice with automatic differentiation. So automatic differentiation is sometimes referred to in this context as backprop, which I'm assuming everyone has seen. It's a required topic in the machine learning class at Berkeley. I believe it's a required topic in most machine learning classes around the world. If you haven't seen this and you're in 282A, make a post on the ed for 282A, and we can point you to resources for it. So why is this great? Because you can express your computation, whatever you want to do, as an analog circuit. You can write it in a programming language as a description of that circuit. And then automatic differentiation will happily compute all the derivatives you ever want or need. And so you can then execute this approach to doing optimization. And that's what you're going to do. So this is kind of very high level. So let's think about what do we want from the circuit. So here, the traditional perspective on these circuits, which is what I think most people have probably seen, but I will emphasize here, is that what you want is expressivity. Right? It should be rich enough with the parameters that you have in the circuit to express the kinds of patterns you want to learn. Now, traditionally, when people thought about this expressivity, and they thought about the patterns of interest, people said, wait, I don't actually know what the pattern of interest is. I can't handcraft a circuit to do what I want. The whole point is I'm trying to learn it. So how do I know that something is going to be expressive enough to express the patterns of interest? And so one of the early approaches that people had to think about this was to, in a way, borrow from an already existing rich tradition in both mathematics and the early theory of computation, which is to say, you know how I know if something can express the patterns of interest? If it can express any pattern, then definitely the one of interest is also expressible. Everyone see that logic there? So it's the same thing that makes people appreciate universal computation. It's like, how do I know this computer is powerful enough to do the thing that I want when I don't yet know how to give it those instructions? Well, it can do anything that's expressible in certain kinds of computational classes. So great. If it can express any decidable thing, hey, that's probably going to capture the class I care about, so good. Okay? Similarly, and much more apropos for deep learning, you have the idea of approximation theory, which has been around. It's like, okay, I want to solve these differential equations. Well, I don't have necessarily a closed form solution for these differential equations. What can I do? Well, I want to express them in some form by which I can do the computation to compute coefficients that will give me approximations to solutions of these differential equations. So let me use Fourier series. Why is Fourier series okay? Because give me enough terms, it's a universal approximator for functions. Again, there's lots of, what kind of functions, So that style. Or, if I have a polynomial, right? Give me a high enough degree polynomial, I can express any function, right, with a high enough degree polynomial. So this kind of style of thinking is what's driving traditional views of the expressivity that's needed here. So patterns of interest. So for example, quote, universal function approximation. So for universal function approximators, you're used to thinking about, presumably everyone has seen things like Fourier series and polynomials as a way of generating any function that you care about, approximating any function you care about. However, to understand neural nets, there's actually a simpler to understand category that kind of conveys the idea more crisply and instantly. So let me think about a specific kind of domain to visualize. So let's visualize functions from R to R, 1D functions. That's the homework, the discussion had you do, look at. Right? And in the discussion, you saw that, look, if I have a 1D function, I can draw it on the board. It's like the only kind of function I can draw on the board, right? Because one is the independent and one is the dependent axis, and then I run out of axes on the board, okay? So as a function, any function, how can I approximate this? So if I asked you, okay, give me a polynomial of some appropriate order degree that will approximate this, you'll be like, yes, I believe this thing exists. Give me a computer and I can grind it out. I asked you, okay, give me Fourier series with some number of terms, a Fourier series that will approximate this function. You'll be like, yes, I know this exists. Give me a computer and I'll grind it out, right? But for one category, you can just draw it, and that is piecewise linear, right? Piecewise linear functions approximate all functions, right? You know that. So you can say, do I have another color? Let's see if it works. Right? I can just put line segments down. Oops. And approximate this function. And you know that piecewise linear functions given enough pieces can approximate arbitrarily well. Okay, any questions on this? Hopefully this is very familiar. This is like way back when you studied things. So the question becomes, how can we think about piecewise linear functions in a way that we can express them using a circuit? Because if you can express a piecewise linear function using a circuit, that we can then have automatic differentiation play nice with, that means we can optimize piecewise linear functions. And that's what you saw in discussion, right? So let's just make sure that we all understand it. So first, before we do that, just a comment. I'm using piecewise linear here. You could say that, wait, actually, I don't even need piecewise linear to approximate. I can approximate using piecewise constant. Right? You know, like I'll lose something. I'll put a lot more. That's how I do like Riemann sums, right? Like piecewise constant, right? So I could use piecewise constant. It's an interesting exercise for you to think, why are we talking about piecewise linear and not piecewise constant? Constant's simpler. And as we kind of go through the exercise of making a circuit for this, we'll see, you know, maybe why. Because remember, we want to express the functions of interest in a way that we can express using a circuit that plays nice with automatic differentiation so that we can use gradient descent style optimization to set those parameters. Right? It does us no good if we break anything along the way. Okay? Because we need stuff to work. Okay, so I will cover this. So one way of thinking about how can you get piecewise linear functions to be expressed is to say, hey, what can I think about piecewise linear functions as being made of? Well, they're made of, here's like a little bit of a twist of how you have to think about it. So one way of thinking about piecewise linear functions that you might have is that they're made of little pieces. Okay? Little segments that are linear, that have a beginning and an end. But there's another way of thinking about piecewise linear functions. So you can think about piecewise linear functions can be constructed from elbows. Put them in quotes. Elbow functions. And what's an elbow function? Something that looks like this. It just goes and bends. Right? So it looks like this, or it looks like this, or it looks like, this is like one example. Here's a second example. Here's a third example. Right? Elbow functions and a constant. Right? If you want to move the whole thing up or down. So does everyone see that? Because you can think of a piecewise linear function. You can think in 1D. I think generalizes in higher dimensions too. You can think of it this way: is you start somewhere, and then you change your slope. Keep going, change your slope. How do you change your slope? Changing your slope is the same as adding an elbow that reflects the change in the slope. Right? Then you keep going, change your slope again. Add another elbow. Change, 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 change. So piecewise linear functions are constructed out of these elbows. So now the question is, how can you express this elbow? So great. This means that if you have an input, x, and you want an output, f theta of x, right? It means as a computation graph, as a circuit, I can put a sum, which has a constant, okay, and a bunch of things that are elbows. where this is some circuit that reflects an elbow. Does everyone see that? This is a way of thinking about it. So now how do I make an elbow? Well, I can make an elbow by saying, so look at one of these boxes. So turns out you can make an elbow by taking an input, multiplying it by some W, adding some B, and then take the result and put it into a nonlinear box, which is just max of 0 and whatever its input is. This thing is called a ReLU, rectified linear unit, which is inspired by diodes. It has two inspirations, actually. It's inspired by a diode because it looks like 0 for below 0, and then 1. So a line of slope 1 after 0. So that's the kind of diode inspiration. And if you want, you can think of this piecewise linear stuff as also inspired by the classical analysis of Bode plots, right? With piecewise linear understandings of things. So either way, it was amply present in the intellectual space for, how do you build these guys? Okay, so first thing that's really important for everyone to understand is why is it that this combination can actually make these elbows? Okay, so let's just make sure everyone's on the same page. So first, let me just kind of touch base and see if everyone's. You saw this in discussion. So you already were doing this in discussion using the computer. And hopefully you'll find the discussion worksheet quite informative in terms of the notebook part, where you can watch how, as you train, these piecewise linear things move around, and the elbows move and adjust. But first I wanted to check, how many people in their ML class have seen this kind of a description of why you get basically a piecewise linear approximation out of this nonlinearity value? Has anyone seen this? Okay, so a couple people. In your ML classes that you saw in neural nets, what nonlinearities did you see? Raise your hand and say something so I can't make out the different things. Someone raise your hand. Yeah. Sigmoid. Okay. What other nonlinearities do you see? Tan H, hyperbolic tangent. What other? Just those? You didn't see this one? You saw this one too?
Yeah.
Okay, but you saw sigmoid first, and then tan H. You say, there's also this guy. Yeah. That's often how it's taught. Different reasons, sociological, cultural, historical. But I personally think this is the easiest way to understand what's going on. So I will stick with this. Because why should a sigmoid result in a universal function approximator? You can grind it out, right? Here it's obvious, piecewise linear. It's all good, right? Derivatives are easier too. Okay, so you look at this and you say, why does this work? So let's look at what this function looks like. So maybe I'll think of this entire thing, because it's parameterized as two parameters, right? So I'll think of this as f wb of x. Two parameters. So this is the circuit view. We can write it out as like math, symbolic math. Max 0, comma, b plus wx. Which is the same. If you don't like the max, you can use ifs. Okay? So what is this? This is the same as wx is greater than or equal to minus b. And now, you have to think about if w is greater than or equal to 0. Okay? Equals if w is greater than 0. Right? Why? Because I need to, by bringing the w over the other side, I got to check which way the inequality goes, right? And if w is less than 0, right, then this whole thing is w plus b if x is less than or equal to minus b over w. Okay? So first thing we notice is that actually, and this you'll often see in the context of deep learning, which is why I'm doing it this way, is that we kind of got it a little bit, like we can't, the way that we've got it set up right now, we can't get this guy, number 2. Does everyone see that? Because we can't get anything to output that's less than 0. Okay? So I need to get this flexibility back of being able to do this. So I can get this flexibility back by looking at my circuit architecture and doing a modification. And saying, so notice, does everyone see that? Like, you try to understand something. You see, can I do everything I can do? Yes, no, not quite. What am I missing? I'm missing the ability to get negative things out. How do I bring them back? Well, I can multiply by a bunch of numbers here. If I allow myself a bunch of parameters to multiply by at the end, then I can multiply by a negative thing and come down. Does everyone see that? Okay, good. So now you have this, and you have this, and you see that, look, the point of the elbow that you get, like where do you transition? This elbow point is minus b over w for that particular one. And what's the slope you get on the other side? Well, this is the case where you have a slope that's less than 0, right? So this is w, and this is w. Two different cases. So if you have a negative w, you'll get this kind of behavior. Positive w, you get this kind of behavior. Either way, the elbow will be at minus b over w. Wonderful. So now you understand this basic case, and you understand what's happening here in terms of you add something on the outside. So this is kind of the prototypical multi-layer perceptron architecture is kind of grows out of this. Okay? Because what you have here is, the way this is viewed is using neural net language. You say, okay, this thing is what's called the hidden layer. That's the output. The things that are coming out of these boxes are the output of the hidden layer. And this is the output layer. And this is just pure, there's no nonlinearity here. It's just affine, right? There's a shift and a bunch of multiplications. So this is called a linear unit, or linear layer. This is the hidden layer with ReLUs. Yeah?
Are we just saying like a wide number of these like are they ReLUs? A wide number of them will approximate any function?
Yeah, so the question is that, what do we know? So you know for 1D functions that if you add more and more pieces, you can approximate functions as well as you want. If those functions are, for example, on a compact set, so the inputs are always in a certain domain. If the inputs are always in a certain domain, a large enough number of these will approximate as well as you want, which means for the perspective of neural nets that when you increase this, it's called increasing the width of the network. This is usually called the width of the network. So it says by making one hidden layer as wide as you want, you can achieve universal function approximation. Okay, that's a great question. So I'll repeat that question for everyone. The question is, this is the class on deep networks. If you get universal function approximation by making one thing wider, why do you need to make things deeper? That question is like the subject and topic of the entire course. Right? Is what, like, why do you need to think about the architecture? And in fact, historically, you might have heard about this. Intellectual disciplines engineering disciplines often go through cycles of enthusiasm, try to make things work, some kind of things start working, and then like people get super excited by them, and then things crash and burn, right? And then like they'll say, okay, maybe we should go do something else for a while. And then they comes back. So I've lost count, but historically, the first golden age of neural nets was kind of in the 50s and 60s. And people were really interested, kind of grew out of an existing base of analog computation, analog circuits. They're like, oh, cool, we can do these and we can make patterns, and lots of work happened. And then there was a paper so before they tried to do things without the hidden layer for reasons of computation simplicity. And then they showed that without the hidden layer, you couldn't achieve certain things. Like, it's not possible. You didn't have a universal function approximator. And then it crashed and burned. Like, okay, stop, this is like too hard. Let's like go do other things for a while. Then, arguably in the late 70s, 80s, there was another resurgence in neural nets, in the interest in neural nets. And in that resurgence, the idea of universal function approximation really captivated people. They're like, oh, wow, this is amazing. We can make it work using wide networks. People tried playing around with depth, too. But, didn't really know how to do it. And there was a lot of fixation on the universal function approximation part. And things worked, and you got advances. And some people didn't really care about the function approximation part, just cared about making things work. But then, again, other technologies became better. given the technological capabilities computationally at the time. And then neural nets again fell out of favor by the, I'd say, mid-90s, because other things were much better at being able to work and also had provable guarantees associated with them and did work better. Then you had the resurgence of interest in neural nets, which occurred, definitely, was a complete breakthrough in 2012, right? And the modern era of interest in deep networks kind of follows from that. And one of the things that happened was actually the shift of the fixation on expressivity towards something else. And so people shifted from really caring about universal function approximation to also caring about the fact that, so the other goal number 2, right, besides expressivity is learnability. Can you train it? For the patterns of interests. Does it actually learn the things you want it to learn? So it's not enough for it to be able to express what you want to express. It has to learn the things you want it to learn. And that's different. Just because something can universally express anything doesn't mean it'll learn the things you want it to learn, given data. Especially given the data that you have. Okay, but before that, I want to make sure we're on the same page with certain terminology. I'm going to express that terminology. So when we talk about this hidden layer written out this way, I will just edit this in place, okay, for simplicity. When you combine this with this, the usual way we think about it is as follows. We replicate the pattern we had over here. That was very natural in terms of how you draw it. So you say, okay, each of these is getting multiplied by some weight. So again, I have to choose a way of doing it. So usually we'll use 2 indices. I forgot what exact order we use in. So I'll just, for now, use the order where I'll describe the layer number first, and then the particular entry. So W21, W22, W2D, B2, 0, or 1. Right? There's only one of them. So this will be W1, 1, W1, 2, W1D, multiplication. And then we add stuff. For reasons that come from circuits, these are called biases. B1, 2, B1D. And then we run it into the nonlinearity, which has no parameters. We want to keep our parameters visible. And by convention, our nonlinearity has no parameters. And the output of the nonlinearity defines the output of the layer, in this case. This is the convention. So these guys are referred to as weights if they multiply things. And if they're added on, they're referred to as biases. Okay? The weight makes sense, right? Bias is a circuit term for biasing circuits. Okay. So far, so good. Any questions on this picture besides the big question of why do we do things that are deeper, which we will build towards? Yeah.
Is there a bigger explanation, why adding the radial layer will increase the expressivity like compared to the linear model because there's no additional parameters. I just have a thinking like.
Okay, excellent question. Let me repeat the question for everyone. The question was, okay, if you think about expressivity as coming from, I'm going to paraphrase your question. If you think about expressivity as coming from knobs to twiddle, it seems that expressivity should be tied to parameters. And sure, we have all these weights, which are knobs to twiddle. We have all these biases, which are knobs to twiddle. We have more weights and more biases to knobs to twiddle. But without these ReLUs here, without this nonlinearity here, the addition, if I just replace these with identity maps, then all I would have is basically all the biases would just multiply through these weights and add to a universal bias. And all these weights would just be like, would go together. And everything I would get is just a single affine function. I get one universal weight and one universal bias. That's it. And I would only be able to express redundantly, using all these parameters, the set of affine functions on one dimensions. But with the addition of the ReLUs, I get all piecewise linear functions. Notice, even in this most natural representation, there is some redundancy. Like this W here and this B are choosing where that elbow is. Right? Does everyone see that? These two are choosing the elbow. But this W and this W together are choosing what the final slope is that gets added in here. We did that originally because we wanted to make sure we got the negative ones in. Right? But it is redundant. You see that? Because between the three of them, there's only two actual degrees of freedom that are being manipulated. Where's the elbow and what's the slope? Like where's the corner, right? So just counting parameters here isn't telling you what the true flexibility is of what you're getting. So the question of, like, why do you need the ReLUs? Well, you can see from first principles why you need the ReLUs. It turns out that generically, the addition of an appropriate nonlinearity here, anything that's like sufficiently nonlinear injected here, will still give you universal function approximation. So you need the nonlinearity to get the ability to express anything. So yeah, again, there's theoretical papers that talk about this, about exactly what this is, how it connects to like concepts like bandwidth and so on. But for us, it's just from first principles we can see it. But the important thing is you can't just naively view the parameter count, the overt parameter count, as the actual degrees of freedom. Even in this example, there's redundancy. Yeah?
When we trained the model to become a universal functional approximator, did that like assume that like it's the number and runs the function infinity?
Okay, great question. Whenever we use the word something is a universal function approximator, we always mean the same way you think about Fourier series as being universal function approximator, which is as you take the limit of number of terms in the Fourier series to infinity, you can approach anything as close as you'd like. Right? Same thing applies for neural nets. When everyone says that this neural net architecture is a universal function approximator of this, it means as you take the width, depth, other things to infinity, it can approximate any function as close as you like. Yeah.
I was wondering if the only thing that matters is that you have a nonlinearity, like why choose ReLU as opposed to something else? Like taking choice of nonlinearity.
Great question. The question is, if it turns out that there's theory saying that you can use other nonlinearities and still have universal function approximation, why do you use particular nonlinearities in practice? Does it matter? And the answer is it matters for different reasons. Okay. First reason is what makes your life easy. ReLU is extraordinarily easy to differentiate. Right? Because you just check. What's the derivative? Right? On this side, it's 0. On this side, it's w with respect to x, 1 with respect to b. Like you can just take these derivatives super easily, right? So it's really, really easy to run derivatives through ReLUs. So that's like a reason to have ReLUs. That's like a practical perspective. As we go, we will talk about other perspectives of desirable properties of nonlinearities for which ReLU will also be nice. So ReLU has another, just since you asked the question, ReLU has another very nice property, which is often useful to us, is that it's non-saturating. Right? If you think about a sigmoid or a tan H or something, they like flatten out. A ReLU doesn't, it just keeps going. So the fact that it doesn't flatten out means that when its derivative will be 0 is just in one place. Other place it looks like it's linear. So that is often useful in the context of larger systems. Now, everything here is about not expressivity. It's about this other part, learnability, which is that's what we're going to talk about. We're going to spend a lot of time thinking about this. How can these things actually learn the things you want? And one of the preconditions of learning the things you want is that it should be able to converge to something useful in a reasonable amount of time. So the fact that things are non-saturating is in part related to the fact that the gradients won't just go to 0 and not move very much. Okay, so with that, I'm actually out of time for today. We'll pick up where we left off and kind of, hopefully you understand this. I guess I should do one more thing, sorry, I should draw one picture since I said it. This guy, right, this is the same as this guy, circuit-wise. Right, so it's just a super simple V in, V out relationship. Yeah. Okay, now, we get questions about the stuff on the board right here, and then we'll walk over to 258.